Hey guys, welcome back. We're going to do lesson 9.2, day 1, and we're just going to go over a couple things and show the notes. So, in the first simulation, we talked about shooting free throws, and this was the accepted truth. I hope that makes sense. Now, yours looks a little different because there's a picture of me right there. So instead of Shaq, it's me, just to be silly. But anyway. I think there is. I'm not sure. I'm at home, so I don't have all my stuff that I normally have, but I think you have this. So H sub O is 0.0. H sub A, we have a sneaky suspicion of something less than that. And that's what we talked about when I discussed lesson 9.1. So thinking about these, each class would find, let's say, a different p-value, because each dot plot would be different, because if each class watched me shoot 50 free throws, then likely that's going to look different each time. So if each class watches me and counts up how many out of 50 I make, then notice this, would it be appropriate to use a normal distribution model? Justify. The answer is yes. The test for normality would be large counts because I'm either making it or I'm not making it. And you actually go by the accepted truth. So even if I don't make, or even if I make 42 and miss 8, even though the actual number in your sampling distribution is different, what's not different is your truth, your accepted truth. So you're using your accepted truth, not actually how many you make. It's how many would you expect to make if this was the truth? How many would you expect to miss if that's the truth? Okay? What other conditions to check? Random and 10%. Now that we have it, what does it look like? So you have this mu p hat. And that just means that if we did a distribution of all these samples, let's say I had tons of, let's say every class you came, I made you meet me in the gym, and we just kept you just kept watching me make 53 throws and counting how many I made. Then the average of the proportion, the average of the sampling distribution should equal the truth if it is in fact the truth. And so this is what we should expect. So this is the average of the sampling distribution should match the proportion of the truth that I made. And so when we do our sampling distribution standard deviation, so that's like if I graphed all these, every day I made you guys meet me down at the gym. If I graphed all these averages, so every dot would be an average of how many I made over 50, right? That's the average part. If it is the truth that my shot ratio is 80%, then most of them would fall a little to the left or the right of 80%. And so I must use this proportion P from the truth, the accepted truth, right? So 0.8 times 0.2 over 50, square root the whole thing. That's my standard deviation statistic. So now it says use the mean and standard deviation. Well, this isn't a mean test, it's a proportion test. But we're saying that the average proportion of all these samples, if we took a whole bunch of samples, the average of the sampling distribution would be our null, right? So kind of this idea of P naught. And then this would be your standard deviation using P naught. Okay, so this is what we should expect from our sampling distribution. And again, you're just imagining that these are all, every single day I made you meet me down at the gym and made you watch and count up how many free throws I made out of 50. This would be our sampling distribution. And we should expect, since large counts worked, that it would make something roughly normal. And because it's roughly normal, we can use a z-score or a normal calculation. So z is equal to actual value. So the actual value we measured, let's say, was that, right, our p hat, minus our predicted. Well, that's the accepted truth, so that's what you should have predicted if that is the truth. And there's my standard deviation. So actual minus predicted over standard deviation. That's where these numbers come from. And we get this number -286. And you might be thinking, well, what the heck am I going to do with that? Well, since it is a z-score, you can be on table A. Or you can use your calculator under CDF. And so we can type this in, normal. Let me get my calculator. Stat, distribution, normal, CDF, lower bound, crazy low, upper bound, 0.64. My mean is supposedly 0.8. My standard deviation is 0.056. Enter. There it is. There's my p-value, a freakishly low normal. So what did I type in? I used the regular old normal CDF, and I reported out lower bound, upper bound, mean, and standard deviation. So notice I'm thinking a freakishly low number, and then that's my upper bound because I'm trying to get the calculator to find the area of the curve. So we do, since this is, since 0.002 is less than 0.05, we do have convincing evidence against the null hypothesis. Okay, let's kind of cut off. So where does that take us? Well, we notice that by doing it by hand, it helps us to think about what it means. So learning target number 1, what are the conditions? These are the same 3. Okay. Learning target 2, understanding that this test statistic, when I'm working with a significant test for P or a significant test for a proportion, is really just using the same Z formula from chapter 2 to come up with, well, what would be the probability of the outcome as least or more extremely likely than that. What does the calculator under the normal calculation use? It technically uses the mean as your p hat, which is your p naught, your accepted proportion, and your standard deviation, and you actually use your p naught and calculate that. So hopefully you notice that's what I did on the back page. What does that mean for the check your understanding? So let's kind of walk through this. Hopefully you tried to answer these questions on your own, and this will provide a little bit more support. So it says a U.S. Census Bureau has a proportion of students in high school that have part-time jobs, 0.25. So that's our accepted truth. And so that's what we write down as our H naught. Now, do we have to, is it okay to stop there? No, because we have to define it. So you have to define what this gobbledygook means. P in this instance is the true proportion of students with a part-time job. And so we're left with assuming that this was the truth or is the truth. And then we get to investigate a little. So an administrator in a high school suspects, so there's sneaky suspicion, that the proportion of people who have part-time jobs is somewhat less. Okay, so that's where we came up with this number. All right. Now, she would like to carry out a test, alpha 0.05. The administrator selects a random sample of 200 students and finds that 39 of them. So let's practice in our calculator. All right, so as we turn this on, we scroll down to stats and we see that we can go to stat test. And what are we doing? Well, we said, do you have a part-time job, yes or no? So this is considered a one proportion Z test. So we're gonna go there. Our P naught is we're supposed to accept that it's 25%, yet the data we collected was 39 out of 200. Okay, now be careful selecting this alternate hypothesis. We have a sneaky suspicion the true proportion is something less than P naught. Enter, voila. So, we got a p-value of 0.03. So that's kind of exciting because our alpha was 0.05. So let's take a look at our steps, and maybe we'll come back to the calculator. So let's take a look. It says, explain why the sample gives some evidence. Okay, well, we said 39 out of 200, which happens to be a proportion of 19.5, which is less, right? It is less. So you have some amount of evidence. You have some amount of evidence that it is less than 0.05. But would that happen if we created a sampling distribution around 0.25 plus or minus this standard deviation anyway? Would that, when I'm saying this standard deviation, let's assuming, how would that outcome come out purely by chance? So first we got to check our normal counts, right? And all's good there. Using our original 25%, we would expect if we asked 200 people, we'd expect 50 to say yes and 150 to say no. And both of those are greater than or equal to 10. Our random sample is random. And our 10% condition is it safe to assume, I don't like how this is written. I've been writing it differently than I've written it in years past. Our pop is as least as large as 10 times the sample size. So I think it's safe to assume if our sample size is 200, there's at least, and if I multiply by 10, there's at least 2,000 students that I'm interested. It's a U.S. Census Bureau, so that there's at least that many students I'm interested in making an inference about. Lots of students in the United States. Okay. So what's next? I did all of my tests, right? Now let's calculate this test statistic. So what is happening in the calculator? It's taking the p-hat, which is this 0.195, minus your p, which is your accepted truth, and putting it over the standard deviation. Now, if you did it by hand, you get this, but it's not really necessary to do it by hand because look at there. The z, negative 1.796, negative 1.797. And we got the same answer. A p-value of 0.036 if you do it by hand, a p-value of 0.036 if you use the calculator. So what is important is you know generally how to do it by hand, not that you necessarily would, and hopefully you're making the right conclusion that our p-value here is less than 0.05. So since our p-value of 0.036 is less than 0.035, we do have sufficient evidence to conclude H sub A, or to support. Therefore, we reject the null hypothesis. We reject the fact that the accepted truth is 25% because we have some convincing evidence that it's something less than that because of this data we collected. That's all, folks. Thanks for joining us.